So welcome back. In the previous class, I have actually discussed about the orthogonal and orthonormal basis. Okay, and what basically we found that if we are able to talk about orthogonal or orthonormal basis, then identifying coordinate using that particular basis is very easy. Okay, so for example, that I have some kind of signal and signal has periodicity 2 pi. So what we found in the previous class, using Fourier series I can able to express that periodic signal in form of trigonometrical function like sin x, cos x, sin 2x, cos 2x, and up to infinite term. Okay, and we are assuming that okay, some kind of signal that will terminate up to n, then I required trigonometrical function up to sin nx and cos nx. Okay, so these are the bases. So once I identify the basis, now suppose I have some kind of a space. So in order to visualize that space, most of time people are taking column vector because we are very comfortable with column vectors. So suppose I have two-dimensional space. So in two-dimensional space we have defined basis like 1 0 and 0 1, and this is orthonormal basis because you can see that they are standard dot product because we are in Euclidean space, means whatever column vector their entry is real number, and distance we are assuming that using the L2 norm I am trying to understand the distance, means suppose I have this point, then a square plus b square is the distance. Suppose coordinate of this point is AB. Okay, so distance from here. So I am in Euclidean space, and after that what basically we are going to do, using dot product we are going to check that dot product is going to vanish or not. If that is going to vanish, then that is called orthogonal vectors. Okay, and after that, in order to check orthonormal, we have to also see the magnitude. So 1 0, so we are going to check the magnitude. 0 1, so I am going to check the magnitude. Okay, and these two vectors form a basis because using these two vectors I can able to represent any point in the two-dimensional space. Similarly, suppose now I have some kind of a space and I am not drawing a space because I don't know the dimension of that, but at least I know that element of this particular space is some kind of function ft, and that function is periodic of period 2 pi. Okay, so I am assuming that now I have different signal of 2 pi, and I am going to express that signal using some kind of trigonometrical function. Okay, so again I can able to identify the basis. So basis is cos x, sin x, one also there, cos 2x, sin 2x. Previous class we have already seen cos nx and sin nx. I am assuming that I am able to represent ft using up to n number of signal. Okay, so now if I am trying to express f1, at that time I need the coordinate. Okay, basis I have identified, and after suppose that I have to represent 5 and 7. So with respect to this basis, if I multiply this as a 5 plus 7, so linear combination of these two I can able to express 5 7. Similarly, in order to identify ft, I have to scale out each and every term of the basis, okay, or basis vector. So identifying the coordinate system is easy if our vector is orthonormal. In previous class we have seen that directly I can able to construct. Okay, so this is one of the basic advantage of the orthogonal or orthonormal basis. Okay, and what we have observed in the previous class, that if I have some kind of orthogonal basis, then just dividing by proper norm. Okay, norm is basically formulated with help of inner product. Due to that reason I am telling proper norm. If I am in Euclidean space, then everything is simple. But suppose if we are not in Euclidean space, so at that time I have to define inner product in some proper way, and corresponding to that inner product I have to find the norm. Okay, and we have already seen in the previous class that whenever I have inner product, so with inner product there exists a norm, so we have to divide with that, and then what happens, orthogonal basis is converted into orthonormal basis. Okay, now next thing is that what we have seen in previous class, at least we convinced the utility of orthogonal and orthonormal basis. Now one of the natural question, how to construct them. Okay, so construction, what we have assumed in the previous class, that I know the orthogonal or orthonormal basis, and then we are trying to identify the coordinate. Okay, but most of practical application, basically we don't know what is the orthogonal or orthonormal basis, but at least by the theory of linear algebra somehow we are able to construct some kind of basis. Okay, most of time that basis is not orthogonal and orthonormal. Okay, so using the help of that some class of basis I am able to identify the coordinate, but calculation or in and a calculation to find the coordinate system is not very easy. Okay, most of time if our signal is very complicated, then using some kind of general basis it is very difficult to calculate the coordinate system. Basically after identifying, means basis gives us one of the way such that I can tell that using that much of minimum number of vector I can able to represent the space. After that, another important thing is that I have to identify the coordinate. Okay, because after fixing the basis, coordinate is unique. Okay, so I have to identify the unique point corresponding to any signal, corresponding to any functions, corresponding to any vectors. Okay, so I need some kind of algorithm such that if I have some kind of signal, some kind of basis, not signal, I have some kind of basis, okay, corresponding to some signal you can tell, or some corresponding to some space, then how to convert that into orthogonal and orthonormal basis. Okay, and that algorithm is actually given by the Laplace. Okay, and later in recently, not I think that around 18th century, basically again that is rediscovered by the Graham Sumit. Okay, and due to that reason this whole process of construction of the basis from any given basis meant that is not necessarily orthogonal or orthonormal is called Graham-Sumit process. Okay, so today we are going to learn that process, and this algorithm is very important because most of time whenever we are doing some kind of signal analysis, okay, in several practical application, at that time I need these classes of basis. Okay, so using this kind of numerical algorithm, okay, one can construct the basis. So now I am going to talk about the construction. So obviously construction is quite algebraic if you able to understand the theory of linear algebra. Okay, if you have idea of basis, if you have idea of linear dependence and independence, then easily you are able to construct that basis. Okay, so understanding the procedure is not too difficult. Okay, so what basically we are assuming, that W denote a finite dimensional inner product space. Okay, finite dimensional inner product space means number of element inside the basis is finite. Okay, that is the meaning of finite dimensional inner product space. Inner product means we are also able to know that how to define dot product kind of things, generalization of dot product, and after that we are also able to know the notion of norm. Okay, notion of norm I have already told you, that gives us the idea that how to talk about the length of the vector. Okay, so now we assume that we already know some basis w1, w2, wn of the w. Okay, so I have some kind of space w, and that is finite dimensional space. So I am assuming that their basis is w1, w2 and wn. Okay, and n is the dimension of the w. Okay, so what is our goal? Our goal, by using w1, w2, wn, to construct the orthogonal basis. Okay, and once I will get the orthogonal basis, I can able to construct the orthonormal too, because that is not difficult process. Just I have to identify the norm, and after that I have to divide each orthogonal basis by that norm. Okay, and due to that reason, means this algorithm is just talking about the orthogonal one. Okay, so let us try to see the process. So in order to construct the orthogonal basis, first step we are assuming that I know some basis. Okay, so suppose that if I have 3-dimensional, 4-dimensional, n-dimensional space, so suppose I have 5-dimensional space. So what you can do, you can construct some kind of 5 cross 5 matrices. Okay, and after that each column of that matrix you can construct such that their determinant not equal to 0. Okay, so if you are able to do that, it means that each column vector is linearly independent. It is possible to show, and that can actually satisfy the criteria of the basis of 5th dimensional space. So construction is not simple, basis construction is not easy, not difficult. So what you can do, you can construct one simple basis, and after choosing that basis, what you can do, you can tell that okay, I have 5th dimensional space, for example, so I have 5 number of column vectors. Okay, if you are in function space, correspondingly you have to tell some relevant information about the basis. So suppose that I have n-dimensional space, I am assuming I know how to define the inner product, I know how to define the norm. At that time, in order to talk about orthogonal basis, what I am going to do, I am going to take the first column vector, and that column vector I am going to define as a v1. Okay, so w1 I know. Now I am telling that v1 is the first orthogonal basis. Okay, so anyone from v1 to vn. So what basically we are doing, we are selecting first vector itself as a orthogonal vector. Okay, w1. So I am telling that okay, w1 is v1, that is orthogonal basis, and with help of that now I am going to construct the second basis. Okay, and obviously v1 not equal to 0, because whenever we are talking that element inside the basis vector, so basis can span the whole space. Okay, so if that is 0, then that cannot able to span the whole space, and due to that reason this assumption is one of the very relevant assumption, that v1 not equal to 0. So whatever element inside the basis, that should be not equal to 0, that should be non-zero, and due to that reason I am assuming v1 not equal to 0. So obviously w1 is also not equal to 0. Now starting with w2, the second basis I am going to construct that as a v2. Okay, so w2 I know. Now with help of w2 I am going to construct the v2, but I am going to construct some kind of orthogonal basis, and due to that reason, and I have already assumed about the first basis v1 equal to w. So what I am going to do, I am telling that whatever second basis that comes into picture, if you take the inner product with the first and second, that equal to 0. Okay, so now what we have to do, I have to use the information of w2. Okay, in order to construct the v2. So first thing, that is obvious from the definition. Now what I am going to do, I am going to define v2 like w2 minus c into v1. Okay, so v I know, c1 is some kind of a scalar I have defined, and now I have to identify this scalar because I know the w2. So I know the w2, I know the v1, v1 is w1, and after that I am telling that v2 is such that that will satisfy this kind of condition. Okay, so I have defined v2 as a linear combination of W2 and V1. Okay, and now I have to identify a scalar for every scalar V1 and V2, their inner product not equal to 0. But if I select C1 in proper way, then it is possible to show that V1 or dot product of V1 with respect to V2 and V2, not dot product, inner product, because I am talking about the generalized construction. So if I am in Euclidean space, at that time I can able to talk about dot product too. Okay, so what I am telling that if I select C in proper way, then I can able to enforce that inner product of V2 and V1 that equal to 0. And I have done the same thing. What I have done, I have used the orthogonality condition, and I am forcing now that V2 inner product with V1 that equal to 0. So now I know that V2, I have just defined V2 like this. I have defined V2 like this, so I am going to substitute that here. Okay, so if you substitute that here, then it is possible to show now that I have, due to linearity property, I can able to expand it. So V2 is now nothing but W2 minus C V1. Okay, so I have applied the linearity property. So due to that, using the help of linearity property of the inner product, I can write the W2 into V1 and C V1 and V1. Okay, so what happens that if you done the inner product with same, then it is possible to show that that is nothing but norm square, because we are defining norm by replacing the another element with same element, and after that we are taking the square root. Okay, so due to that reason I have written here V square, and in this way now you can see that I can able to construct this C. Okay, so once I able to construct the C, then I am able to tell that V2 is another orthogonal basis. Okay, now since C I have constructed, W2 I know, W2 information is given to me, V1 I have assumed that is W1, so I can easily able to construct the V2, and in this way I can able to construct the second orthogonal vector from with the help of W2 and V1. Now it is possible to show that V2 not equal to 0. Why? Because V1, W1 and W2 are linearly independent, and V1 I have defined as a W1. So by the help of linear independence, it is possible to show that V2 not equal to 0. So please do by yourself. Okay, that is very easy. Now suppose I have to construct third basis. Okay, so how to construct third basis? In order to construct third basis, again now what I am going to do, W3 I know, V1 and V2 I have constructed, so I am going to use that information, and now I am going to coin two scalars C1 and C2, and again the property of orthogonality I can able to evaluate that scalar. Okay, and I have two information now, because V1 V2 I have constructed, so I know that dot product of V1 or inner product of V1 and V2 equal to 0. So I have this kind of information I have, and after that I am going to enforce that inner product of V1 and V3 that equal to 0, and V1 and V2 that V1 and V2 and V3 that equal to 0. Okay, so using the help of these two conditions, I am going to actually discover the value of C1 and C2. These two value I am going to discover. Okay, and here you can see that that is very easy process. So in this way, suppose if I have to, from here algorithm become clear. Suppose if you want to discover C1, so C1, try to see that C1 is nothing but the multiplication with V1. Okay, and due to that reason, now in order to calculate the value of C1, W3 you know, you can take the inner product of W2 with respect to V. Okay, and after that divide with the corresponding norm. Similarly you can able to discover the value of C2. Now W3 with V2 and take the norm. Okay, and in this way it is possible to show that, again I can tell that since V1, V2 and W3 all are linearly independent, so V3 not equal to 0. Okay, so now suppose that you write this algorithm, okay, with help of some software, and suppose in some way if you are selected w1 w2 w3 as a some kind of linearly dependent element, means that is not form a basis. So it is possible to show that somewhere inside, whenever you are going to proceed, then v1 v2 v3 some quantity becomes 0 and your algorithm will terminate. Okay, so there is no need to check that w1 w2 w3 all are non-zero if all are linearly dependent or linearly independent. You can start with any. Okay, what happens that if they are linearly dependent, then automatically your algorithm is terminated. Okay, now similarly I can able to generalize it for any order. Okay, so I have n dimensional, so each time whatever knowledge you have, using that knowledge you can construct the next one. Okay, and in that incremental way I can able to construct the whole basis, and this general process is called Gram Sumit formula, and that is given like this. Okay, so applying this formula is not so difficult. I hope that you are able to understand how basically one can construct this formula based on the help of the notion of inner product as well as the notion of norm. Okay, so for example, for simplicity, what I have done, I have taken a column vector. So whenever you have column vectors and each entry is a real number, you can able to talk about dot product because this form Euclidean space. Okay, so either you can talk about norm, any other norm, or a standard dot product you can take. Okay, then also you are able to construct the base orthogonal basis. Okay, so what I have done, I have taken the R3 space and I have told you that why this is R3 basis of R3 space. You can construct some kind of matrix with help of this basis and just check the determinant. Okay, if this determinant is not equal to 0, then you can tell that these are the basis of R3. Okay, now please check that is orthogonal or not with respect to a standard dot product. So w1 dot product w2, it is possible to show that that is non-zero. Okay, now what I have to do, I have to construct some kind of orthogonal basis. Okay, so in order to construct orthogonal basis, what I am going to do now, I am going to use the Gram Sumit process. Okay, so in order to apply that process, I have to understanding that how to construct the algorithm. So in the algorithm construction, we have already understood that what I am going to do now, three basis element I know. So first basis element I am going to define as a v1. So same kind of things I have done here. You can see that v1 I have defined as a w1. Okay, so first process is very simple. After that, with help of v1 or w1 you can tell, because both are exactly the same, and with help of w2 now I am going to construct v2. Okay, another orthogonal basis. So what I am going to do now, w2 I am going to substitute. I know the w2, I know the v1, and we have just seen that in order to calculate this c, I have to take the inner product of the w2 with respect to v1 that is known to me, and after that I have to define after that we have to divide with the norm, standard norm. Okay, a square of this. So now you can see here that since we are in Euclidean space, so I can able to take a standard dot product. So with help of a standard dot product I can calculate this whole term, and that is given by this, and after that I have substituted this and I will get the next orthogonal basis. Similarly, I can able to construct the third one. Okay, so please do by yourself. Okay, now I have told you that once you get the orthogonal basis, then one can easily able to construct the orthonormal too. How to do that? You can just, since here I am in Euclidean space, so Euclidean space I can able to take the standard norm. So what you can do, once you constructed the orthogonal basis, so here orthogonal basis is now v1, v2, and after that I have orthogonal basis like v3. After that, what you have to do, you have to just check their magnitude and you have to divide with that magnitude. similar kind of things I have done. I have calculated the magnitude, and please divide this V1 by norm of V1, similarly V2 by norm of V2, and V3 by norm of V3, and these three can form the orthonormal basis now. Okay, another important thing is that with help of this algorithm you can also able to construct some basis of the subspace. Okay, so when I was teaching the vector space, at that time I have already told you that subspace is some kind of subset which has vector space kind of property, or they will satisfy all property of the vector space. So now suppose that I have some kind of subspace, and I am assuming that subspace is the omega is the some kind of vector space, and that belongs to R4. So what I am assuming that I have 4-dimensional vector space, and omega is basically a subspace of 4-dimensional vector space. Okay, and I am just going to take those kind of vector which is orthogonal to the given vector like this. Okay, and for that I have to construct the basis. Okay, orthogonal basis. So problem statement is I have 4-dimensional space, so inside the general basis I have 4 element. Okay, now what I am telling that I have some kind of vector in that 4-dimensional space. So since vector in 4-dimensional space and I have Euclidean space, so 4 components should be there. So you can see by counting this is transpose. So 1 2 3 4 component. So I can convince that this represent the 4-dimensional space. After that, what we have to do, I have to create some kind of subspace such that this subspace is going to consist of those vector which is orthogonal to given vector. So now what I am assuming that general orthogonal vector, it might possible I have more than one. So that form is given as x1, x2, x3 and x4, and using the help of orthogonality condition, since we are in Euclidean space, so I can use the dot product, standard dot product. So after taking the dot product of two vector, I can able to form this kind of algebraic equation, homogeneous algebraic equation. So you can see that I have just one equation and I have 4 different unknowns. So if I fix 3 unknowns, then it is possible to show that 4th unknown is itself known, because they are all linear combination equal to 0. And due to that reason, now arbitrarily what you can do, you can substitute x2, x3 and x4. So actually if you see that this particular algebraic equation is actually algebraic equation of this subspace. Okay, and in order to create this subspace, now I need 3 bases only. Why 3 bases? Because 4th one is the linear combination of all 3 independent one. So either you can select x1, x2, x3, x2, x3, x4, or any three you can select. Okay, so subspace has now dimension 3. Okay, so original space is R4, now subspace in R3, and I have to identify the basis of the R3. Okay, so we have constructed some kind of basis that is not orthogonal. Okay, so I have constructed basis such that they will satisfy this equation. Then only I can tell that this particular subspace is perpendicular to given vector this. Okay, now I have to construct the orthogonal basis. So in order to construct orthogonal basis, again I can apply the Gram-Sumit process. Okay, and how to do that? You can start with first vector. Again, by using dot product, you can construct the C1 and substitute C1. In this way you can able to get the V2, and lastly with the construction of C1 and C2 you can able to get the V3, and in this way I can able to construct the orthogonal basis. And in order to construct the orthonormal basis, what you can do, since you are in Euclidean space, so you can calculate the magnitude and just you can divide with that. Okay, In this way, I can able to construct the orthonormal basis too. Okay, it is possible to show that. So this is one of the way to write the algorithm. Okay, same construction algorithm, Graham Sumit process, you can construct in another way also. Okay, so I am going to also give the overview of that. So why I am giving too much emphasis on this, because whenever you are trying to do some kind of mathematical modeling analysis, anything, you have to select the coordinate system. And how to select coordinate system? So you have to select the basis. Okay, and if you have basis vector, then easily you are able to construct the coordinate system. Okay, and due to that reason, you have to understand that how to convert the some general class of basis into orthogonal and orthonormal basis. Okay, so second is just the modification of first algorithm. So what basically we are going to do now? So we have seen that general step of construction of the algorithm. So suppose that if I am on first place, so k equal to 0, if you substitute, then this is gone, and after that k equal to 2, if you substitute, then v2 I can write that w2, and after that here I have summation from j equal to 1 to 1, so w, so I have c1 and v1, like that. Okay, so in this way I can able to construct the whole orthogonal basis. Okay, so what basically we are going to do now, whatever basis, first basis v1 that is arises, I am going to divide with that their magnitude. Similarly, second, then I can going to divide with their magnitude. So in this way I am going to do the normalization. Okay, and after that, what happens that I have w1, w2, w3, wn. Okay, and u1, u2, u3 I have already defined. u1, u1, u2, u3 I have already defined. In this way I can able to construct the triangular system. Okay, and I can easily able to identify r1, r11, r22, r13, r23, r33, like that. Okay, so please see that how to basically we can proceed. So again, since we know that wj and uj both are orthogonal to each other, so I can able to, what I can able to do, that I can able to take their inner product, and after that I will see the inner product. Okay, if you see the inner product, so all u1 is orthogonal to u1, u2 is orthogonal to u3. In this way, what happens? Only one component is going to remains, because these are directly orthonormal. So orthonormal means their magnitude is unity. Due to that reason, I can able to construct Rij. Okay, so Rij, in this way I can get the Rij, and after that what we have to do, I can, in this way I can get the Wj, and finally what happens that R11 I can able to get W1. Okay, and by setting R11 equal to W1, I can able to construct U1, and similarly subsequent stage I can able to construct U2, Uj, like this. Okay, so please go through it. This is not so difficult. Again, this is very simple algorithm. Okay, and in this way general step is that Uj you are able to construct like this. Okay, with help of one example I will explain. Okay, what I am going to do, suppose I have again same three vectors. Okay, and now I am going to construct some kind of orthonormal basis directly. Okay, so again I am in a three-dimensional space, and if you see the each entry, so each entry is just a column vectors. Okay, and column vectors, each entry is the real numbers, and I can tell that this is nothing but a Euclidean space, so I can able to deal with the dot product also. So r11 I have constructed that w1, so square root of that, and u1 in this way I can able to construct. So first orthonormal basis I have construct, and after that what I am going to do, I am going to do the next step. So in next step, r12 I have to construct, and w2 and u1 I am going to take the dot product or inner product. In this example this is dot product, and r22 similar way I can construct, and after that I will actually to divide, and in this way I can able to find the orthonormal basis directly. Okay, so up to here what we have seen, that if I have some kind of a space, and inside the space, if element is represented in form of column vectors, in form of functions, then how to talk about orthogonal or orthonormal basis. Okay, orthogonality is also important if element inside the space in form of matrices. Okay, so I have already told you that whenever we are talking about vector space, so element may be in form of the matrices. Okay, so now we have to define, obviously we have to define some kind of concept like orthogonality in case of matrices too. Okay, so we are trying to see that what is meaning of orthogonal matrix in case of the space where element in form of matrices. Okay, so matrices whose column form a orthonormal basis. You can see that I am not telling that orthogonal only, orthonormal basis of Rn relative to the standard Euclidean dot product play a distinguished role. Okay, and that particular matrix is basically a orthogonal matrix. Okay, so first we will give the definition of orthogonal matrix, and we are assuming here for simplicity that each entry of matrix is just a real number. Okay, now if you see the application of orthogonal matrix, so they have huge application in geometry, physics, quantum mechanics, crystallography, partial differential equations, symmetry theory, and special function. Okay, so in today's lecture I am not going to talk about each and every application, but you are able to find these kind of application for orthogonal matrices. Okay, so now one of the most important application, that is in rigid body dynamics, that rotation matrix in three-dimensional space, that is described by the orthogonal matrix. Okay, and hence they are lie at the foundation of rigid body. It is possible to show that if you are able to identify the rotation matrix, then you are able to identify the angular velocity. Okay, because what is basic limitation in one dimension? Suppose that I have some kind of mass here, and if that is rotated about this point, and if I know the theta, so angular velocity I can define that d theta by dt. Suppose if we are in higher dimensional space, two-dimensional or three-dimensional space, so at that time rotation is function of theta phi psi. Okay, and at that time you cannot tell that rotation in one direction is theta dot, one direction is phi dot or psi dot. If you see rotation in one direction, that is also function of another two angle, and at that time I need the help of rotation matrix to talk about the angular velocity, and that is very important whenever we are dealing with satellite aeroplanes, drones, underwater vehicle, or computer graphics or animation. Okay, and due to that reason, role of orthogonal matrix is very useful for the practical system analysis. Okay, that is also from the computer science point of view, mechanics point of view, and another chemical industry, as well as the electrical and electronics industry. Okay, so how to define orthogonal matrix? So I am assuming that I have some kind of a space, and what I am assuming now, that a space, each entry is represented in terms of matrices, and where each element of row and column is just a real number. Okay, and at that time, or some function of real number you can assume. Okay, and after that I am going to define the orthogonal matrix. So a square matrix, so whenever I am talking about the orthogonal matrix, at that time we are limit ourselves on a square matrix only. Is called orthogonal if they will satisfy this kind of condition. Means q transpose q equal to q transpose equal to identity, then I can tell that as a orthogonal matrix. Okay, so what happens that in several practical application, people found that this kind of matrix appear. So due to that reason, they have given some kind of name for that, and after that, with existing theory of the column vector, they are trying to identify that what kind of basic property is actually involved inside the orthogonal matrix. Okay, so that property I am going to identify using this proposition. So what this proposition is telling, that a matrix Q is orthogonal if and only if its column form a orthonormal basis. You can see that what we are telling, that if their column are forming a orthonormal basis with respect to Euclidean dot product. Okay, so in on R3, then only I can tell that as a Euclidean, then only I can tell that as a, basically this is nothing but Rn, that as a orthogonal matrices. Okay, so in order to define orthogonal matrix, now I have to take help of orthonormal column vectors. Okay, and I have to take the help of Euclidean dot product. Okay, so let us try to see why we are claiming this. So let u1, u2 and un be the column of Q. So whenever I have matrix, so I can interpret that matrix as a some form of column, collection of or column vector. So I have defined collection u1, u2 up to un. Okay, and transpose of that will gives us the row. Okay, row of the transpose matrix Qt. So I have this matrix, and if I take Q transpose, then actually what happens, that their row become column. So this will give us the rows, and if you see the ij entry of that matrix, so that will give the row of Qt, and means ith row of Qt and jth row of Q, and I have to make sure that this condition will satisfy, and if this condition is satisfied, then I have to force ui and uj. If I equal to j, that should be 1, otherwise that should be 0. Okay, and whenever this kind of condition I have, so I can tell that it means that ui and uj equal to 0 and ui and uj equal to 1. It means that u and uj both are orthogonal vectors. Okay, column vectors, and due to that reason we are claiming this kind of things, that a matrix Q is orthogonal if and only if its column vector form a orthonormal basis. Okay, so now whenever some matrix is given, so in order to confirm that is orthogonal matrix, now I have to just focus on the column, and I have to check that these two columns are orthonormal or not. Okay, so let us try to construct one orthogonal matrix. Okay, so you can see that in order to construct orthogonal matrix, I have to construct some kind of orthonormal column vectors. Okay, and what kind of norm we have to use? We have to use the Euclidean norm. Okay, so I have here two columns. Similarly, you can construct 3 cross 3 matrix also, that is more involved process. So what, by definition of the orthogonal matrix, I have to make sure that Qt transpose Q, that should be identity. Okay, and if you do Qt transpose Q, and Q I have selected, that is ABCD. Okay, so same kind of things I have substituted here, and after that now you can see that I am going to equate with 1 0 0. So this should be 1, this should be 1, and these two should be 0. Okay, so I have 3 equations, and first 2 equation, if you see carefully, since we are in 2-dimensional space, so these two should be lie on the circle, unit circle. Okay, I can interpret that these A and B are some kind of point, general point inside the unit circle. Okay, so I can select A as a cos theta and C as a sin theta. Similarly, B as a cos phi, or cos psi, or D as a sin psi. Okay, and after that we have to also force AB plus CD equal to 0. So from AB plus CD equal to 0, you are able to establish relationship between psi and theta. Okay, and because I have to force cos theta minus psi equal to 0, so due to that reason, if I select psi, that is given like this, then I can tell that this condition will also satisfy. Okay, so now what happens, that I can able to change this psi by theta. So if you replace psi by theta plus half pi, then you are able to get that some kind of things like minus sin theta. Okay, so I have two choices. Either I can use plus sign and minus sign, and due to that reason I have two choices: B as a minus sin theta or B as a sin theta. Correspondingly, I have D as a cos theta and D as a minus cos theta. And in this way, I can able to construct 2 cross 2 orthogonal matrix, that is cos theta minus sin theta and cos theta. And another one is like this. And since I am assuming that during construction this kind of relationship is used, and due to that reason I am restricting myself on theta that lie between 0 to 2 pi. Okay, so try to see the interpretation of this. Suppose I have some kind of point here. Okay, and now I have represented that point using 1 0 0 1 like this matrix. Okay, now suppose this particular coordinate system, so I have this coordinate system, you can assume x1 0 and x2. Now if I try to represent same point P using x dash 0 and x2 dash, it is possible to show that this coordinate system is converted into this system. Okay, so directly it means that orthogonal matrix tell us that if coordinate system is rotate, so how actually point is changing. Okay, similarly if you see here, then this will gives the rotation in the another direction. Okay, so if you have any confusion, then please let me know. Okay, now it is time to conclude the lecture. So what we have actually found in today's lecture, that if I have some kind of basis, okay, so from that basis how to construct orthogonal or orthonormal basis. Okay, after that, for that what we have done, we have used the Gram-Sumit algorithm. Okay, two form of Gram-Sumit algorithm we have used, and later we have used the same idea. Using that same idea, but suppose that now I know that how to construct some kind of vectors which is orthogonal to each other. Okay, so now suppose I have to define the orthogonal vectors. So in order to define the orthogonal matrix, so in order to define the orthogonal matrix, what we have to do, we have to make sure that each column that should be orthonormal. Okay, and what we have seen that orthogonal matrix has several applications in the practical system, and due to that reason we have to learn that how to construct the orthonormal matrix, orthonormal column vectors to construct some kind of orthogonal matrix. Okay, because in orthogonal matrix what we found that q transpose q equal to q transpose, that should be identity. Okay, so each element also to form the unity. Okay, and obviously some extra condition comes into picture, so I have constructed the 2 cross 2 orthogonal matrix. Okay, so if in this way orthogonality is one of the most important property. Okay, now if you have any question, then please let me know.